the relative amounts of acid and base. One factor that influences how effective a buffer is the relative amounts of the acid and the base. So the buffer will be most effective when the concentration of the acid, the weak acid, and its conjugate base are equal. So to show that, let's look at two 1-liter solutions of a generic buffer. This has a pKa of 5, and we're going to calculate the percent change in pH when 0.010 moles of sodium hydroxide are added to these solutions. So here we've got the first solution, equal moles of the acid and the conjugate base. The initial pH is 5 because that's the Ka of the solution. So before addition, we've got 0.1 moles of the acid, 0.1 moles of the conjugate base. When we add 0.01 moles of sodium hydroxide, that is going to react with the acid, and so we're going to lose 0.01 moles of the acid, so we'll have 0.09, and then we'll gain 0.01 moles of the base. So now we have moles of acid, moles of base. Because this is a buffer, we can use the Henderson-Hasselbalch equation. So pH equals pKa plus log of the base over the acid. Now these are in moles, but it's a 1-liter solution. The molarities are the same. And even if it was a different volume, the volumes are the same, and so they're going to cancel out in this ratio. So the pH here will equal pKa, which is 5.00, plus the log. We've got 0.110 moles of the base, 0.090 moles of the acid. I'm coming up with 5.08. So that's the pH. We're going to look at the percent change. So the percent change is a percent delta. So we're going to take the difference between the initial pH and the new pH, divide by the initial pH, multiply by 100. So that's 1.7%. Any questions? So I'm looking at the percent change in pH. So the initial pH to the new pH, that difference divided by the initial pH. So there's not really anywhere to write that. pH initial minus pH final divided by pH initial times 100. That's going to be the percent change in pH. So our second solution, we have 0.18 moles of the acid and only 0.02 moles of the base. So this is not equal amounts, not even close. So here we've got the acid and the base. Again, we're adding 0.01 moles of hydroxide. So that's going to reduce the moles of acid and increase the moles of base. Again, we're going to use our Henderson-Hasselbalch equation. And now the concentration, 0.03 for the base divided by 0.17 for the acid. That 5 is the same because that's a pKa, and we're looking at the same buffer. So this is going to be 4.2466 and 4.25. The reason we're looking at the percent change is they started out at different pHs. So the percent change is more meaningful. So the percent change here, that would be this new one, 4.25 minus 4.05 divided by 4.05 times 100. And then we get 6.2%. So 6.2% versus...
If it's initial, wouldn't you be 4.05 minus the 4.25?
How's that? Absolute value.
Okay.
So this buffer is not as effective. Adding the same amount of base, the pH changes significantly more for solution 2. Yes?
Why was that 5 the same again? Is that just because of...
That's the pKa.
Okay, it's just for the solution.
Yeah. So for the weak acid, that 5 is going to be the same. See here, the initial pH was 5, and so then you can kind of get confused and think that, well, maybe that's the initial pH, but it happens to be the same there because these are equal concentrations. When a buffer has equal concentrations of the acid and the base, its pH is equal to its pKa. And that's why the pH here is different, because we have more acid and less base, and so the pH is lower.
But the pKa happens to be the same.
But the pKa is the same because it's the same compound. Any questions? Yeah.
Where was the pH used, the given pH used?
The given pH was just used when I calculate the percent change.
At the very end?
Yeah. Just looking at the percent change.
Just as the initial?
Yeah, I'm using the initial pH and comparing it to the pH after adding the base. See which one changes less.
And those Ka values are always given in a table?
Yeah, they'd be given to you. Mm-hmm. For this one, you're getting 4.9. I might have done it wrong. Yeah, I did do it wrong. I did something in my head, which I should know better. I did 0.25 divided instead of 0.20. So you are correct. It should be 4.9. 4.9%, still higher, but thank you. Any other questions? So the relative amounts of acid and base are important. So we can determine that for a reasonably effective buffer, the concentration of the acid and the base should not differ by more than a factor of 10. So in other words, the ratio of the base to the acid should be greater than 0.1, less than 10. If you look at one of the concentrations, the other one should be no more than 10 times higher, no more than 10 times lower. And that's just sort of a ballpark rule of thumb sort of thing. The absolute concentration of the acid and its conjugate base also affect the effectiveness. So if we have a buffer where we may have equal concentrations of the acid and the conjugate base, but both of those concentrations are very low, the buffer is not going to be very effective. If the concentrations are high, the buffer will be more effective. So we're going to look at that same buffer again. So the pKa is 5.0, but now solution 1 is going to have concentrations that are 10 times higher than solution 2. We're still going to add 0.01 moles of sodium hydroxide and see what the change in the pH is. So here we've got 0.5 moles of each. So this is nice. We've got equal quantities. So this is going to be effective, and its pH is going to be 5. Over here, we also have equal amounts of the acid and the base, but they're 10 times lower, 0.05 instead of 0.5. Because they are equal, the pH is equal to the pKa. So we've got our little addition tables here, starting with 0.5 and 0.5 and adding this. So we're going to end up with 0.49 moles of the acid and 0.51 moles of the base. So we can plug that into our equation. The new pH will equal the pKa plus the log of the ratio base to acid. So 5.0173, call it 5.02. So then the percent change is 0.4%. Very small change. Over here we've got the same sort of table, just different starting concentrations, and so then the ending concentrations are going to be different as well, using that same equation. Remember, this equation can only be used when x is small. It does make things a lot faster. So 5.1760. 5.18. .6. So the percent change is almost 10 times higher when we cut the concentrations by a factor of 10. So the relative amounts of acid and base matter, we'd like those to be equal or close to it. And then the absolute concentration matters as well. Higher concentration gives a more effective buffer than a lower concentration. We can calculate the outermost points of the effective range of a pH buffer. We said to be effective, the concentrations of acid and base should differ by no more than a factor of 10. So if we say, well, the lowest pH is where the base concentration is equal to 0.1 times the acid concentration. The base concentration is 10 times lower than the acid. So we can look at that equation, the Henderson-Hasselbalch equation. Every time I say Hasselbalch, I think David Hasselbeck, right? It's just not something I need to be thinking about. So pH equals pKa plus the log of the base concentration over the acid concentration. Well, here the base concentration is 0.1 times the acid concentration. So that's the base concentration. The acid concentration is, well, the acid concentration. Those cancel out. And so we get pKa plus 1. No, minus 1. Guess what's going to happen with the high pH range? Well, here the concentration of the base is 10 times higher than that of the acid. And so we get pKa plus 1. So we can look at the pKa for a weak acid and identify, well, is this going to work as a buffer for the particular pH that I need? The pH that you need, that you want for your buffer, should be within 1 unit of the pKa of the weak acid. So the effective range is 1 pH unit on either side of pKa. So you want to match up the desired pH as close as you can to the pKa of your buffering acid. Then you can tweak the pH a little bit by adjusting the ratio of acid to base. Any questions? Well, here's a practical question. Which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? If you have 500 milliliters of a 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? Well, we're going to choose the acid based on looking at the desired pH. The desired pH is 7.35. So is hypochlorous acid going to work? 3.74? No. This is far too low. The pKa is far too low from the desired pH. This one's also too low. The only one that's even close is that was hypochloric. That was chlorous acid. This is hypochlorous acid. 7.54. That is within 1 of 7.35. So this is the acid we want to use. Yeah, choose a pen. This is the acid we want to use. Okay, so we want a pH of 7.35, and then we have to figure out how much of the sodium salt to add. So Henderson-Hasselbalch equation again. Whoops, that's not an equals, that's a plus. Log of the, so here the base is going to be the ClO minus, and the acid is HClO. We know what pKa is, we know what the pH is, we know what the concentration of the acid is, it's given right here, so we can calculate the concentration of the hypochlorite ion. So pH is 7.35. That's going to equal 7.54 plus the log of the thing we want divided by 0.1. I'm going to 7.35. I'm going to subtract the 7.54. So I get negative, negative 0.19 is equal to the log of these two things. Then I need to get rid of the log, so I'm going to do 10 to the x to both sides. So 10 to the negative 0.19. Equals that. So I'm going to take 10 to the negative 0.9 and I'm going to multiply by 0.1. And I'm getting this ion concentration 0.645. Oops, I lost a 0. So that's the concentration of hypochlorite ion that I want. Now this becomes more of a Chem 1A problem. I have 500 milliliters of this solution, and I want it to have this concentration. I have to calculate the mass of the sodium salt. So it's 500 milliliters. So I want 500 milliliters of 0.064. So 0.5000 liters times that concentration. And this is a place where you definitely want to keep a couple of extra significant figures to avoid rounding errors. And then I need the molar mass of this guy. Sodium and chlorine and oxygen. $74.44. So I'm going to multiply by my molar mass. And I'm coming up with 2.402 grams. So now 2.4 grams of the sodium salt. Any questions? So we've talked about the effectiveness of a buffer. Buffer capacity is the amount of acid or base that you can add to the buffer without causing a large change in pH. So that's going to increase with the absolute concentration, also increase as the relative concentrations of the buffer components become more similar to each other. Sometimes you know that your buffer is going to have to withstand mostly added acid or mostly added base, and then you'll stack the buffer so that it has more of the appropriate component so that it can have a larger capacity.